galvanizers and our current president. Before he joined PSE, he enrolled in Western Governors University. He graduated in October with the Bachelor of Science in Computer Science. His speech today includes a demo of his capstone project. The first part of the speech will be an introduction to neural networks aimed at a general audience, whether you have a technical background or not. Neural networks are on the cutting edge of artificial intelligence, used for everything from Google Translate to Facebook ad algorithms. It is a method for letting the computer software train itself to do very complex conceptual tasks, such as handwriting recognition, speech recognition, molecular binding for pharmaceutical companies, and predicting behavior for Facebook and political campaigns. As the name implies, the concept was to model how the human brain itself uses neurons to learn. The talk will demystify what they are and how they work. Now, the second part is the demo, the use of neural networks in making predictions in foster care adoption, using what he calls the adoption alacrity dashboard. As both a foster and adoptive dad, this combined his interest in AI with his passion for foster care. Please be aware that this is a computer science project, not a social work thesis. This is a demonstration of how the technology can be applied. While some components of the school assignment were fictional, the technology is real and the data he used is also real. Neural networks can model for virtually anything about which we have collected data, including foster care, to answer important questions. Please help me welcome Gary Malkasian, Introduction to Neural Networks and Their Use Making Predictions in Foster Care Adoption Outcomes. Gary.
Thank you, Madam Toastmaster. At, at, cat. We all learned that in kindergarten, right? Except that's not the way you learned language. Your mother didn't say to you as a baby, "Oh, are you hungry? Want your ba-to-to-oo?" Yeah, she didn't do that. She just said bottle, handed you a bottle, and you figured it out. In fact, not only did you learn language, if you had been consistently exposed to 10 different languages, you would have learned them all fluently. In fact, in 4 or 5 years, your baby brain would speak all 10 with a fluency greater than I could learn any one of them with my adult brain in 10 years. This, in fact, is pretty amazing. Can you see my slideshow? No, there we go. There we go. This is pretty amazing. When you came into this world, your brain knew nothing. You didn't know language. You didn't even know language was a thing. More fundamentally, you didn't know how to process light, how to detect sound, how to hear. My wife says I still don't. How to process sensory information at all. The 100 billion, with a B, billion neurons in your brain that you were born with were constantly bombarded with electrical impulses from the 7 trillion nerve cells distributed throughout your body. They are sending electrical impulses representing light, sound, taste, fragrance, heat, pressure, and so on. But you didn't know any of that. You were just flooded with a lot of data. And somehow your baby brain figured it out. Now, modern neuroscience has a very sophisticated theory to explain how this happens. It's known as IDK. LOL. I don't know. Nobody knows. That's the whole point. Nobody knows. What we do know is that there are different areas in the brain which seem to respond. We do know that the nerves here, here's a picture of a nerve, gets activated by some event, like a photon of light hitting it, or the hair in your eardrum wiggling because of a sound wave or some pressure. And that generates electricity, which sends an impulse up the dendrite to the next nerve. And then there's a long daisy chain of nerves going all the way up to your brain. And if all those nerves were stretched out end to end, it would go on for 90,000 miles. All these messages coming into your brain create a tremendous activity. There's a complex internetworking of messages going back and forth, transmitting back and forth. For example, let's say that we wanted to model this somehow. Let's take a look at this set of neurons that I've drawn. I didn't draw 7 trillion, I only drew 15. We're going to say that those two red ones in the end, those represent inputs. Okay, well, let's say that the top one is sound and the bottom one is vision. All right, and maybe you're watching a television program. Each of those neurons, and there wouldn't be just two, there'd be millions of them, but each of those neurons would then send its information to several other neurons. And each of those neurons would be receiving information from several neurons. And they're doing some processing, we don't know what, they're doing some processing and they're passing it on to the next group, and so on. Until it gets all the way to the end. We're going to call that last neuron, we're going to call that the output. That is the semantic event where your brain suddenly realizes, ah, there's a cartoon dog playing a piano. But we don't really have a clear idea of what that processing is, which brings us to artificial intelligence. For years, the prevailing theory within AI was if we could simply deconstruct everything down into rules and find logical ways to combine these rules and then teach them to the computer, then the computer could learn things. If we could deconstruct language into phenomes and vocabulary and grammar and teach it all these rules, then the computer could learn language. This was an adult brain approach. All right. And it had problems because people would form words different ways. You'd have different accents. But we thought, well, if there's any failure, it's simply because we haven't broken it down far enough. We need to account for the individual linguistic kinesiology of each person, not just accents, global accents, but even regional differences, or even within the same house. People who grew up in the same house can speak differently. Why is that? If we could just figure that all out. Well, using this approach, if you could get up to 70, 75% accuracy in speech recognition, that was considered pretty good. Today, using the neural networks, the state of the art is like 98.6, which is pretty amazing. Because you think about it, with the different accents and things, you didn't have to learn different accents when you learned language. You didn't. A Frenchman doesn't say to the baby, no, little baby, we are French, we nasalize, it's wah, wah, wah. No, they don't do that. They just talk as the baby understands, and eventually the baby does. So how are we going to model these different relationships? Well, how do we model anything? In computer science, let's start with an equation. Here's the equation of a line. You might have learned that in high school geometry. If you forgot, don't worry about it. Just the idea is you take a number, you multiply it by something, you add something to it, and out comes an output. We're basically going to extrapolate that for activation. Instead of X, we're going to use A. A is the activation. That is the value of the neuron. So for the nerve cell, ow, that hurt. That is an activation. All right, that creates an electrical impulse. The value in the nerve, the level of the electrical impulse is going to be the A. How much attention I pay to it, that's the W. Right now I'm talking. I don't have time to pay attention to what's going on with my hand. So I'm talking to you. And then the bias would be the B. And we're going to set this up and we're going to have an equation for each of these relationships, as you can see as I'm doing on the board here. You get this whole mess. But don't worry about this whole mess, okay? The computer will keep track of the equations for you. All you need to remember is that you've got inputs and you've got an output. And in between, we're going to call those neurons the hidden layers. And there are relationships between each of these neurons, creating a big inner network, and each of these relationships is governed by an equation that looks something like this. All right, almost something like this. Because for neural networks, we want to have our values be between 0 and 1. So we're going to squish them. So we're going to use the Greek letter S for a squishification, and we're going to create a squishification function, right? There are many different functions that have been used to do this. The one that's currently used, at least it's the most popular now, it's one of the more popular ones, is called the ReLU. Basically, that's just a fancy way of saying a line. It's a rectified line, rectified linear units, all right? Think of it this way. When you were in school, if you got below 60% on a test, that was an F. They didn't give out G's and H's, okay? Oh, you only got 5%, that's a Q. No, they don't do that. You had to get up to a certain level before they even start tracking. Otherwise, they're just gonna say, you're not even in the ballpark, all right? Now you're getting a little bit closer, blind man's bluff. We don't start saying you're warm until you're in the right section of the room. And it seems that this way it works out a whole lot better. I want to go to a handwriting. So one example of this is like handwriting recognition. Take a look at these pictures. Let's say I want to read the numbers, the account numbers you're writing on a slip of paper. Pretend each of these squares is a computer screen. I break it down into pixels, and each of those pixels we're going to break down, and we're going to put it through that big complex series of equations I showed you at the beginning. And you may be asking yourself, wait a minute, okay, I understand the A's, but what about the W's and B's? How do you know what W's and B's to assign? We are going to use the time-honored tradition of baby brains. We are going to guess. To think about it, isn't that what a baby does? A child doesn't simply look around and say, oh, I have observed my parents walking. I have now learned ambulatory bipedal kinesiology. I can walk and start walking around the room. That's not what happens, right? The child, she kind of pushes herself up. She takes a couple faltering steps and she falls flat down on her can or on her face. And what do the parents do? They come running over. You're such a big girl. Good job. I'm so proud of you. That was your first steps. They heap rewards on her. Turns out the same thing works with computers. Now you might be asking yourself, what do computers like as rewards? Well, it turns out they like the same things we like, chips and cookies. That was just a joke. That was just a dumb joke. Most of my jokes have some meaning, that one didn't. So we take our wild guesses and we push it through and we come out with some number at the end. Okay, let's say that the number I want is the number 2. If I'm just wildly guessing what all these constants are supposed to be, what are the odds that I'm going to get the right number at the end? It's practically 0, right? Let's say instead of 1 output, I've got 10, and whichever one lights up, that's where we're saying that it's most likely that that's the digits that the person drew. All right, you see this particular one, it's all over the board. So we're going to do something called a cost function. It doesn't matter that it's wrong. It doesn't matter. What matters is that we can measure how wrong it is. We know what it's supposed to be, and we can take a measurement. And because we really want to accentuate the problem here, we're going to square the difference. Yeah, we're not just going to tell you a difference. We're going to square it, and then we're going to add them all up and say, you got a 3.1. That was bad, okay? You do not get a reward for that. Far Side cartoon. Bad dog, no biscuit. Let's say it gets a slightly better response. Okay, now we say, oh, that's a little bit better. Now the cost function, it's still off. Okay, we still got some that are lit up that really shouldn't be. And we're not all that firm on the one that actually is correct. But the cost function with this would be maybe a 0.05, much closer. Okay, good dog. You get a biscuit. Good computer. We can take this and we can measure. We create this function and we can actually graph it out. Now, for those of you who remember college calculus, there's something called a derivative. We can figure out where the minima and the maxima are, because that's what we're looking for. We're looking for the minima. We're looking for where it gets to 0, where the difference is 0. All right. Now, if I told you don't have to be technical for this lecture, so hey, if you don't know college calculus, that's okay. Just rest assured, baby brains somehow are doing calculus. That's right. It's like we're taking what's called a drunk walk. All right. We take a step, we move in the direction that we think is down, and then we take another gradient and we see, okay, where should our next step be? So each step along the way, I measure which way goes down the fastest based on taking a derivative, and then I take a step in that direction and then take another measurement. Eventually, it's going to zigzag around a lot, but eventually it's going to get to the bottom. All right. But take a look here. It's going to get to pretty much guaranteed a local minima. It will not get to a global minima. If you're on the left side of the screen, you won't get to the global minima. But you will get to a minima. Okay. We start doing all these different, lots of different dimensions. In this case, I've got 3 dimensions. My neural network had 1,200 neurons in each layer, which would be 1,200 dimensions. That's a lot. Okay, I'm not going to draw that, but the math is the same. The question is, how can we get to the global minima? Well, taking this drunk walk, clearly the problem is we need more drunks. Let's say we take 1,000 drunks and we parachute them in all over the county and let them start taking their drunk walks. That's basically what we're doing with something called the genetic method, which takes, let's say instead of 1 neural network, I'm going to make 1,000 of them. And I'm going to let them all run, lots of iterations. And then we're going to evaluate. The 500 that are the worst, delete them. The 500 that are the best, clone them. Do some random mutation of the W's and B's and kick them off again. And do this repeatedly. And there are statistical methods that will show that that will get to the global minima. So, let me go back. So we're going to take a look at our cost function, and it's going to tell us how we're going to bump up our W's and B's. And we're going to average it out over all the data and try to come out with the best answers we can. But we're still going to have some error. What do we do with that? We're going to push it back. We're going to, so the blue row is going to tell the pink row, listen, I wouldn't have to twiddle with my W's and B's so much if the activations you're giving me were not so crazy. So you need to twiddle your W's and B's. And so it will. And it'll just push that error back until it goes all the way back to the others, and then eventually it'll come out with something. Now, the amazing thing is that this seems to work. Like I said, state of the art now is like 98.6. I am going to go to, so you can read this later in your leisure. I'm going to go straight to, there it is. This is my dashboard. This is what I call the adoption alacrity dashboard. This tab represents the descriptive method that I was required to create a descriptive method. That means basically take the data and display it. Now, the data I used was from the Children's Bureau of the Department of Health and Human Services, part of the US government. And I had data from all 52, I know there's not 52 states, but we'll say 52 because I'm including District of Columbia and Puerto Rico, even though they're not officially states. And going for 5 years, from 2012 to 2016. So on this tab, you can pick your state and you can pick your year. And it's kind of interesting if you do that, because you can kind of pick a particular year and you can just go and see all the differences between the different states. I had data on gender, prior relationship. Prior relationship could mean foster parent. You see, most of these are either foster parents or other relative, but they could be stepmother, stepfather, an aunt that does the adoption, a grandparent that adopts. Interesting, on the family structure, most people are married. Married couples, you do have single males, single females, and unmarried couples as well, but it depends on the state. And then also interesting, which children are selected as special needs. Now, a couple of words about the data here. Look, you see Ohio, virtually all the children are special needs. Washington, 100% of the children are special needs. New York, 0% of the children are special needs. What are the odds of that, okay? What we're looking at here is a difference in definition. They're defining special needs differently. For that reason, I did not include special needs in my model. I just left it out because that data, I couldn't really figure out what a true special need was. Besides which, what is a special need? Are we talking a physical disability, a mental, a behavioral, what? You can pretty much say every kid in foster care has got some special need, just because of the trauma of being in foster care. That's basically what Washington State says. So every kid gets it. Adoption subsidies, we're also looking at. We're looking at race, and we're looking at race. We had Black, African, Asian, Black or African American, Asian, Hispanic, white, and also, let's go to Hawaii. You have, there we go, Native Hawaiian or Pacific Islander. You only find those in Alaska and Hawaii, pretty much. These are some of the problems I had with the data modeling. Was that for a good neural network, you want your columns to be unrelated to each other, all right? Whether you're in what, identify as one race or another, that is not unrelated, okay? Your family structure is not unrelated. So what I wound up doing was simplifying this by saying, okay, I'm not going to look at every slice. I need to draw some limits somewhere. I'm going to look at either you're a relative or you're not. I've got something binary there. I'm going to look, are you married or you're not? So I'm going to put the single male, single females, and unmarried couples into the same. And the reason I did that was I could look at the data and say, that pretty much is what I see in the data. You're either married or you're not. It seems to be pretty clear. And with race, wasn't so easy. But again, I looked at what do we got as far as race. Obviously, 60% white. I mean, you have a very high number of kids that are identifying as white. That obviously is a population we need to look at. I know from my experience in Washington State, 30% of the children in foster care are either identified as Black or Native American. Okay, that far outstrips the representation of those two populations in the general population. So clearly that's something we need to look at. And even though there's not a lot of Hispanics in Washington State, there are some, but not too many. I mean, not too many in foster care. Okay, I'm just talking about the children in foster care. There are very significant numbers if you're going into the southern states. So I basically built my modeling around those four. What I did was I created 4 different neural network models, and you have to choose which model as a user you're going to use. I also needed to create essentially a regression. I needed to show, create a hypothesis, and then I had to test my hypothesis. My hypothesis was that if you get a large adoption subsidy, then your total between TPR and adoption was going to decrease. What is TPR? TPR is termination of parental rights. It's the last step before a child is free for adoption. Unfortunately, if a child's been in foster care for a long time, as in more than 18 months, 2 years, 3 years, my kids, it was 5 years, okay? That's a ridiculously long time to be in foster care and not have any emotion. At some point, you need to say, we need to move forward with this child's life. And there is a legal process, an actual trial that takes place unless the parents agree to do an open adoption, as my kid's mother did. So anyway, so my hypothesis was that if you had an adoption subsidy, that would decrease the total time of it takes to adopt a child. And you can see that based on the data, my hypothesis is disproven. And you can kind of see why. You take a look at those dots, they're all clustered right above the 95% mark there. Pretty much everybody's getting an adoption subsidy, right? So there's not a lot of variation in that. And because I was having fun with this, I went ahead and tested other things that weren't in my hypotheses. I created graphs for other. So does being married change how fast you go from TPR to adoption? How about the age of the child? Black, male, female, African American, Hispanic, since I had those models in there, Native American or white. You do see some, like in this case, it seems that if you're Hispanic, it looks like it's a very weak correlation, but there is some correlation that says you do seem to get to from TPR to adoption a little bit faster. I don't know what to make of that, but there it is in the data. Okay, and finally we get to the predictive model. This is the artificial intelligence part. This is, I'm simply loading the data from Kentucky. This is the actual historical data from Kentucky. And you can see the different percentages there. And let's say I want to say, okay, that is what it really was in Kentucky, but let's say I want to change it to Nevada. How would Nevada handle it if they had to deal with Kentucky's caseload? Okay, so you can change that. We can change, let's say that only 85% are going to get a subsidy. And let's say, you got to select a race. Which racial model do you want to use? Let's say we're going to go with Hispanic. Okay, let's say that you see there's 8% Hispanics there, 92% non. Let's say they had 50% Hispanics. How would that change? And then we hit the prediction model, predict button. And this is the part that was actually using the AI to come up with a prediction of how that would affect the average time between TPR and adoption. And this is the artwork of Jeff Willis, because I didn't want to just see a gauge going by. It shows you a little graph there. So this is not the Holy Grail. The Holy Grail is reducing a child's total time in foster care. I was dealing with aggregate data, which is the data I had available, and looking at the time between TPR and adoption. But what this shows you is that we can make fairly accurate predictions. In this case, it's a bit odd. Well, it went from 11 months to 12 months. I found that it was about 90% accurate, which when you consider is actually pretty good. When you look at the size of the buckets, the buckets I had were like 3 to 4, 5 months in size. All right. The average is 11 months, which means the error was 1 month, about 1+. Okay. We can't be more accurate than the initial data we started with. So getting 90% I thought was pretty good. That is my demonstration. I think the bottom line here, though, is that I'm going to show you again. Let's see, from current slide. No. Yeah, there we go. This is that. I'm going to skip all paths. I have got a bunch of, you can see the repos of my work out on GitHub. I will send this out with, I'll send you a link. You can download the PowerPoint. You can look at these at your leisure if you like. Also some links if you want to learn more. It's got links also to Jeff Willis's website. And here's something else I got out of my project. I got a diploma. Yay! Bottom line here for neural networks is that when it comes to learning, baby brains kick adult brains in the medulla oblongata. Thank you, Madam Toastmaster.
Oh, I love it. Thank you, Gary. Let's take 1 minute, and if I could get Ariana 1 minute on the clock, please provide Gary some feedback in the chat feature, just a few words, feedback, encouragement, what if he was to do this again, maybe a word or two or something. So please go ahead and give him some feedback. Thank you. All right. Thank you, Ariana. Katie, obviously we're a little late in time, so we're not going to have time for our table topics, but that's okay because our featured speaker was fantastic today. Thank you very much, Gary. We're going to bring up our evaluator for Gary, which is Katie Larson. Katie?
Thank you, Madam Toastmaster, fellow Toastmasters, guests, but especially Gary. As I said before, I will tell you some things I thought you excelled at, a couple things you might want to work on, and how to challenge yourself in the future. First of all, really impressive networking and promotion of this speech. You have a really, really great turnout. I haven't quite seen anything like it since I've joined. I really liked how you introduced your guests before you handed it off to the Toastmaster. It helped them feel welcome and it gave us the opportunity to know who was here. I really liked your introduction that Karina read. It really set the stage for your speech. You had a good intro with the cat. It's very attention getting. I really like the theme of baby brains throughout your speech. It helped me understand some of the information you were giving me. The slides went along really, really well with what you were saying, and the visuals on your slides were well picked. The most impressive thing I think about this speech is how knowledgeable you are and how you presented that knowledge. Also, you didn't seem to be extra nervous because are 30 people here, and that is impressive. Very, very well done. Things you may want to work on. I would suggest not pulling up your PowerPoint until you're ready to start referring to the slides. It seems that it might have been on another screen, and so when you were looking over there, it could be a little bit distracting. I wonder if there is a way that you can kind of line it up with your camera. Your transition between certain parts of your speech, you said anyway, and that could imply that maybe we didn't need the information you provided, or it can negate the context that you said prior to that. So just keep that in mind next time you speak. And finally, to challenge yourself, I would say between ideas, maybe pause for a little bit longer so we can soak in the information, slow down a little bit. You can always ask for more time for your speech if you feel rushed. And lastly, I would have liked to know how many hours you spent on this, or maybe the biggest challenge. But all in all, this was a very, very interesting speech, and I look forward to hearing from you again. Madam Toastmaster.
Thank you, Katie. What a wonderful evaluation. I would like to get our report